Okay guys, so far we studied about the, you know, simple harmonic motion using spring mass system. So is there any other system which exhibits simple harmonic motion? Any other example? So another example is that exhibits simple harmonic motion is pendulum. Okay, so let's look at this. I got this here cork ball, have this thread. You guys probably have used this before in 201, or maybe not. That's also okay. It's kind of long here, so I'm gonna just make it shorter. Okay, so then you can see it, and then this is recorded in the video. So this here, if we leave this up, here, this pendulum here, it has some length, right? It has a length, some length L, and then there is this mass here, and then now let's set this in motion. Okay, so we have this here. This is our equilibrium position for this one. Okay, when it's here, right here in the middle. Now if we leave this, let's take this all the way up here. What is happening as we are going up this way? It shouldn't be touching. Okay, now it's kind of rotating. That's not what it is supposed to do. So it should be in the same plane. Let me try it this way. Maybe this is better. Can you guys see this here? Maybe you can better. Okay. Alright guys. So if it's okay, so now you guys can see this, right? So this is going back and forth, right, back and forth, so it's repeating, right? So again, repetitive motion. So this also, pendulum also exhibits simple harmonic motion. Let's try to draw this guy here. So instead of my hand, usually we put this in something, maybe something like this here, and then let's see, this is the, so this is the length L, and then we are hanging some mass here, right? So this has some mass M, okay, and it's going, it's moving like this, and it moves through, and then there is some angle theta here. Okay, so there is the angle between this normal and then this pendulum here, right? Okay, so it's kind of like this. Can you guys see this? It's like this basically. Let's make it almost in here, and then it goes here, and this is like this. So this theta. Okay. So for this pendulum, do you think we could use a similar approach, or really same thing like the spring mass system? What do you guys think to describe the motion of this pendulum here? So yes, in fact we can do just a little bit of changes in the spring mass system equation, and then we can actually just study the motion of this pendulum. However, this is very important here. So in practical or in real life, this motion we just had, simple pendulum, it exhibits simple harmonic motion only for a small angle. So that theta, if theta is very large, then it is no longer simple harmonic motion. Okay, but then if it's a small change, a small angle, if this if there is a small displacement, a small angle displacement, then it exhibits simple harmonic motion. So again, if you are doing some simulation in the computer, because then you could this system would exhibit simple harmonic motion even if it's for a longer, even if it's for a larger angle, because really, right, in simulation what could go wrong, right? It's supposed to be the perfect ideal. But in real life, however, this pendulum exhibits simple harmonic motion only for a very small very small angle theta. Okay. Oh, I have something here. Let me see. So I have something here. I'm going to write this down here quickly for you. So there is this, this is moving through some distance here, right? So let's say this, arc here, it goes back like this. That is, let's make really this is like length S, and then there is this force, right? So if some force there, that is, let's call the tangential force, that's going to take it back to its original position, right? Equilibrium length here. It turns out that Ft, tangential force, is equal to minus mg by L times S, okay? So S is again the arc length, okay? S is, I'm going to write this down, where S is arc length, L is length of pendulum, okay, and G is acceleration due to gravity or free fall acceleration, and M is mass, right, mass of the pendulum there. This T here, T represents tangential motion, okay? So T means just tangential, right? This force is really tangent to this curve. So it's kind of like this, guys. It's like this. You got a curve here, and then the motion is like this. That's the tangent, and this is the Ft here. Okay, and the curve, this curve has S length, okay? So arc length, right? S is. So let's call this equation, and this equation valid for a small angle, right, as we just said before. So this equation, does it look like somehow the equation we had for spring mass system to you guys in some way? Okay, let's look at this. We got some force here on the left hand side of this equal sign. We got the negative sign just like the one we had in the spring force equation. We had something here, we don't know, mg by L, something that has to do with mass, that has to do with the property of this material here, or the pendulum itself, and length also property of the pendulum. In the spring mass system we had a K, and then S is arc length. Earlier we had stretch or elongation, right? So this quantity here, so wherever we have K in spring mass equation, so if we replace K by mg by L in spring mass equation, in spring mass equations, then we can use everything for pendulum. Just we can use all the equation we use for our spring mass system for this pendulum as well. Okay, so what does that mean? Then it is easy. So then what do we have here is then our position versus time graph. In this case the position is the arc length, right, that change in this arc, right, S here. So instead of xt we can write st equal to A cos 2 pi ft, okay, and r, this is for the arc length, or we could also do for the displacement of angle, okay. So theta t could be written as maximum value of theta, theta max, and then cos of 2 pi ft, okay. So now there is not much to replace here, right, for the position versus time graph here. This is for, you know, position versus time, okay, function. However, now let's look at something we looked at earlier. For frequency of spring mass system is given as what? 1 over 2 pi square root of m by, what is it, square root of k by m, right? So, oh, wait, let me see. I do k by, right, square difficult by k. That should be the, let me check that. I make a mistake sometimes there. Okay, not, yes, k by m. Okay, so this is correct. Okay, so let's replace k by this quantity here. F equal to 1 over 2 pi is square root of, in place of k we are going to write mg by L, this place divide by m. Okay, so you see this m and this m gets cancelled, so we end up with frequency equal to 1 over 2 pi square root of z by L, okay? Really very similar to what we had for, this was for a spring mass system, right? So this was for a spring mass system. Here again you see frequency depends upon what? The free fall acceleration, and the inversely depends upon the length of the pendulum, right? So we can see that if we, so there is going to be larger frequency if we have a very smaller length of the pendulum, and then if we have a larger value of free fall acceleration or acceleration due to gravity, okay. But then we'll have a very small frequency if we have very long pendulum, length is very long, meaning this L is going to increase, right? So it will have a very small frequency, okay. And also if we have a very small gravity, right? So instead of just being in the earth, you will happen to go to the moon, which has 1/6 time of the 1/6 time of gravity of the earth, then you will have smaller frequency, okay, assuming you are taking the same length of the pendulum. All right, so that is about this. So now if we have this f, we can also find the equation for time, right? Time period t equal to what? 1 over f. If we do that, what do we get here? So t equal to what? Inverse of this. So you just make everything inverse, right? Or you could just bring everything down here, so that should give us what? 2 pi square root of L by Z. So this gives us the time period of the simple pendulum. Alright? Sorry. Okay guys, so what do you think, is there any other thing that we can think of, any other situation where the system exhibits simple harmonic motion? Have you thought about your leg, your arm? Look at this. When I'm walking, look at this. Sorry, that's not what I wanted to do. This is not part of the simple harmonic motion demo, okay? So this one, look at this. arm going like this. If you're walking, when we walk, look at our arm, or look at our feet when we are walking, or we can even, we don't even, well, you cannot see my feet, but look at my arm, okay? Or you can try your own arm. So this also exhibits simple harmonic motion, but we don't call this a simple pendulum, okay? We can consider, something like our hand, which is, which has this repetitive motion. It exhibits a simple harmonic motion. Such kind of pendulum which has its mass distributed along its length, right? So I have, length of my hand, mass is distributed along this length. This kind of pendulum is called physical pendulum, okay? So, physical pendulum. So, physical pendulum is going to look something like this, right? So let's say, I have something here to show it to you. So maybe I'll just show it to you, and then we'll continue with the equation in the next lecture. Okay, so this one also can be like a physical pendulum, right? I have my ruler here. It is very convenient. It has a hole here. So let's say if I try to actually, let me try to do this. No, I can just make this one better. Or let's look at it. Okay, so now we have this hanging here, right? This has some length L, but then it has its mass distributed along its length, and then we can also let it go like this, right? It should not be going that circular motion, okay? So that's important here. It should be moving in the same plane. Oops, that didn't come out. Oh, maybe my hand is better. I just saw, I thought anger would do better, but maybe. Okay. So it's supposed to, you guys got the idea, right? So it also exhibits simple harmonic motion. Okay? So physical pendula, I'm going to kind of draw this over here. And then we'll start the other in the next class. So let's say we have a pivot point here, and then this pendulum is like, kind of, I'm just making this big, but I'm going to draw it here for more. So maybe make it like this. Like this, okay? And then this is where this pivot point, and then we got, really it should be, let's make that like that, pivot point here, okay? And then it has a length L, it has length L, but let's call the distance from this point all the way here, this distance as D, okay? And then now this is the center of gravity, right? This point here is the center of gravity. So it's really due to the moment of inertia, right? We'll have a torque in this system. So this torque, rotational, this torque is going to try to bring this back to its original position, okay? So torque, somehow the moment of inertia must be responsible for its for simple harmonic motion, okay? And in the next class we are going to continue discussing about simple harmonic motion, specifically for physical pendulum, and then we'll also talk more about different other type of oscillation like damp oscillations and so on. Thank you guys for watching this video. Bye bye.